So today we're going to be talking about resonance in circuits, and we are going to specifically focus on series resonance for today. So let's say that we have a simple RLC network where all of the elements are connected in series like so. And this is part of some greater network. I'm going to define this voltage V across the terminals of my RLC portion and this current I flowing into the terminals of my RLC portion. And we're going to look at the input impedance of this network. So the input impedance is just the impedance seen looking in through these terminals. So Zn as a function of j omega, we're dealing with a steady state system, would be R plus j omega L plus 1 over j omega C. What up? Thought I heard some. Okay, sorry. And I'm going to choose to express this in rectangular form by lumping my imaginary parts together. So that would look like omega L minus 1 over omega C, right? Because we know that 1 over J is the same thing as negative J in the numerator. So resonance in a circuit is defined as the frequency at which the imaginary part goes to zero, or another way to think about it is the frequency at which the impedance behaves as if it were purely real. So pretty obviously then, in order for this circuit to be at resonance, the positive reactance of our inductor has to be exactly canceled out by the negative reactance of our capacitor, right? So for resonance to occur, Zn must be real, which implies omega L has to be equal to 1 over omega C. And we can do a trivial amount of algebra to see then that resonance will occur at a frequency of omega is equal to the square root of 1 over LC. And we call this frequency the resonant frequency of the circuit. This agrees exactly with the resonant frequency for a series RLC system that we determined way back in circuits 2 when we were looking at this from a context of transient analysis. Literally getting the exact same result because it means the same thing. Okay. So the frequency at which the impedance of the circuit is purely real is known as the resonant frequency. At resonance, the voltage drop across our network and the current flowing through our network are in phase, right? They are completely in phase. So what I'm going to do here is I'm going to plot the input impedance as a function of frequency, and we can see a couple of things here. So this will be the magnitude of Zn as a function of omega. And then we can also plot the phase angle as a function of omega as well. So let's say at approximately 4 units out, this will be our resonant frequency. So for the magnitude of our impedance, we should have a curve that looks something like this. It's going to decrease until we hit omega naught, and then it is going to turn around, and we should see that our impedance is simply R, the real part of the impedance at our resonant frequency. So we can see very obviously that our impedance is at a minimum at resonance, right? If we were to look at our phase angle, if this corresponds to negative 90 degrees and this corresponds to positive 90 degrees, we would cross through 0 degrees at exactly our resonant frequency. So we would have something that looks similar to this, right? So it's going to start off at negative 90 degrees for very low frequencies because the capacitance is the dominant portion of the impedance. As we get closer and closer to our resonant frequency, the resistor takes over. And then as we go beyond our resonant frequency, the impedance of the inductor becomes the dominant contribution to the system. And that's exactly what we see over here on the left-hand side as well, right? We know that for a capacitor, the impedance is going to look more and more like an open circuit. So at DC, we see very, very high, or closer to DC, we see very, very high impedance because the capacitance is dominating, gradually decreasing until we hit our resonant frequency. And then when we get into high frequencies, the inductance looks more and more like an open circuit, which is why our impedance gets larger and larger and larger. Right? So now let's take a look at what's going on in terms of energy storage for a network at resonance specifically. Okay. So, or actually, before we do that, does anybody have any questions about what resonance means? Okay, nobody's asking anything. Yes. So, I know how an inductor and a capacitor behaves, right? So an inductor, or excuse me, so let's start with a capacitor, right? So capacitors at DC look like what? Open circuit, right? And an inductor at DC looks like what? Short circuit, right? So I'm going to have some very, very large impedance from my capacitor, some finite impedance from my resistor, and then effectively no impedance from my inductor when we're at low frequencies, right? When I get near my resonant frequency, the whole point of resonance is that the positive reactance of my inductor exactly cancels out the negative reactance of my capacitor. So the only thing that's left is effectively my resistance. And then for larger frequencies, right, since we know that the impedance of a capacitor is inversely proportional to frequency, so as omega goes up, the impedance of the capacitor goes down. As we get higher and higher in frequency, the capacitor looks more and more like a short circuit. Transversely, since inductance is directly proportional to frequency, as we get higher and higher in frequency, the inductor looks more and more like an open circuit. So we effectively have the exact same condition that we had for low frequencies, except the role of the capacitor and the inductor have switched. Is that sufficient explanation? All right. Any other questions about resonance and its simple effects to this point? All righty. So energy storage. All right. So let's say that we have a very simple circuit, just an RLC network once again, and we are going to excite it specifically with a voltage source operating at the resonant frequency of the system, right? So this is our Vs of t. I will define it in a moment. Here we have some resistance R, some inductance L, and some capacitance C. let's say specifically that Vs of t, it has just some generic magnitude Vm cosine omega naught t. And to make the math easy, let's say that the phase angle is 0. Right? Since we're dealing with energy storage in an inductor, we obviously need to be keeping track of the current flowing through the inductor. So let's define that here as IL of t. And because we're dealing with the energy storage by a capacitor, we need to be keeping track of Vc of t as well. Right? So here we have Vc of t. So I hope I don't need to draw this out in the frequency domain, but I'm happy to. We would just replace L with j omega L and C with 1 over j omega C. So let's start by figuring out what the inductor is doing, okay? So at resonance, what should our current look like? So in the frequency domain, our current IL should just be our phasor voltage Vs divided by R, right? Because we know that at resonance, this impedance and this impedance cancel each other out. Okay. So we are simply going to have Vm divided by R angle 0 degrees is our current flowing through our network when we are exciting this circuit at its resonant frequency. In the time domain, then, our inductor current, IL of t, will just be Vm over R times the cosine of omega naught t. The energy stored by our inductor is 1/2 L times the inductor current squared. So that's going to look like 1/2 L times Vm over R cosine omega naught t quantity squared. And this is going to look like Vm squared L divided by 2R times the cosine squared of omega naught t. Because we're dealing with energy, this would be measured in joules. So everybody with me thus far? No wild or weird trig identities or anything like that yet. Hopefully not at all, but we can pull it out if we need to help us understand things. All right, so we found our inductor current, use that to find the energy stored in our inductor. Now we need to figure out what our capacitor voltage is going to be. How would we go about doing that? It's not a trick question, or I hope it's not a trick question. I think I heard somebody say Ohm's law. If you did, you're correct. Shouldn't be any harder than that. We know what our impedance is. We know what our current is. V is equal to I times Z. Seems like a perfectly reasonable explanation, right? So our phasor capacitor voltage is going to be 1 over j omega C times our phasor current. Because since we have a series RLC circuit, our inductor current is the current flowing through the capacitor as well. And so from here, this is just going to be 1 over j omega naught C, because our circuit is operating at resonant frequency, times Vm over R with an angle of 0 degrees. And so this is going to look like Vm divided by omega naught RC with an angle of negative 90 degrees. And just as a quick aside here, that's going to allow us to write our capacitor voltage as a function of time as Vm over omega naught RC. Since our phase angle is exactly negative 90 degrees, I'm going to call this sine omega naught t. And from here, the energy stored by our capacitor, WC of t, is 1/2 C VC squared, or 1/2 C times Vm over omega naught RC sine omega naught t quantity squared, or Vm squared divided by twice omega naught squared R squared C times sine squared of omega naught t. Just to be clear here, I'm not missing a square on the C because I have one in the numerator and then C squared in the denominator. They cancel each other out. So, all right. So what I'm going to do now is I'm going to plot this stored energy as a function of time. Okay. So recall very quickly what cosine squared looks like, right? So cosine squared is going to be 1/2 plus 1/2 cosine of twice omega naught t, using that same boring trig identity that I used over and over and over again way back in circuits 1. Okay. So if I plot things here, my maximum value should be 1. My minimum value should be 0. So let's do our cosine function, or our inductor energy, as it were, in red. So something like this. What's sine squared going to look like? Well, we could convert both of those sines as cosine of minus 90 degrees. And then when we do that part where we effectively are adding the two things together, it's going to look like cosine of twice omega naught with a phase angle of negative 180 degrees. So effectively, the energy stored by our capacitor is going to be 180 degrees out of phase with our inductor. I just realized that I skipped a part, so I'll have to go back around to that in just a second. And I'm kind of normalizing things here, so messing things up a little bit, but we'll fix that in just a moment. And I apologize for that. All right, so let me fix something really quickly here. So this maximum value, I had it as 1, but that was just for cosine squared. Realistically, we should have Vm squared L over twice R here, which is where the maximum value of the inductor stored energy should be. This actually is also the maximum value for the capacitor stored energy. Let me prove that to you really quickly, right? We have Vm squared over omega naught squared R squared C. Well, omega naught squared, or really 1 over omega naught squared, is just going to look like an LC in the numerator. And so the C is going to cancel things out. I'm missing, hold on. Let me go back 1 second here. Yeah. my apologies, I'm missing a squared on that R from here. And so when I have an LC in the numerator right here to get rid of that omega naught, the C's are going to cancel each other out, and I'm going to wind up having Vm squared L over twice R squared, which is the exact same magnitude. Okay. So let's talk about what's going on with this energy storage. Effectively, we have almost like an electrical pendulum. Okay. So when our inductor's energy is at its maximum, our capacitor's energy is at its minimum. As the inductor starts to lose its energy, the capacitor starts to gain whatever energy was lost, until we get to this point here, where all of the energy that was stored by the inductor has been given up to the capacitor, and then that system or that cycle occurs over and over and over again, right? So for a half cycle, our capacitor is the energy storage element, and it's transferring all of its energy to the inductor. And then for the next half cycle, the exact opposite is happening. So energy is just constantly being transferred back and forth between the capacitor and the inductor when our system is at resonance. Okay. What is the total energy stored by this system? So somebody said 0, and intuitively that kind of makes sense, but it's wrong. Okay. So notice here that our graph stretches from 0 up to some finite value. If I add these two curves together, how am I ever going to get 0? No. In fact, when I add these together, I'm just going to get this constant value. So if I put this legend here, where this is WL as a function of time, and this as WC as a function of time, this purple curve will be WS, where that's just stored energy, and that's going to be WL plus WC, and it should look perfectly constant. So the total energy stored in our system is a constant value, and we can prove this mathematically very easily, right? So WS is going to be WL plus WC, which is going to look like Vm squared L divided by twice R squared cosine squared omega naught T plus Vm squared L over twice R squared sine squared omega naught T. Since I have a constant term, I can factor it out. So Vm squared L over twice R squared times cosine squared plus sine squared. Sorry, that should have a T there. Go away. We know that this thing right here is simply 1. So we just get Vm squared L divided by 2R squared. And I'm going to call this capital WS because it is effectively a DC term now. It's constant for all time when our circuit is operating at resonance. So this is the amount of energy stored in our system at any given point of time. Yes, sir.
Where does the D go? From 1 over 2 over 5?
All right, so let me scroll up here. So we know that omega naught squared is 1 over LC, right? So I can get rid of this omega naught squared by putting an LC in the numerator. This C cancels this C, And I have the exact same magnitude for both the energy of my capacitor and inductor. Okay. Any other questions for this part right here? So this is our total energy stored. Yes, sir.
WS on all.
That's correct. It's a constant value, not related to time one bit. Pretty interesting situation going on here, right? We have signals that are oscillating in time, but our energy stored is very specifically constant. All right, so now let's look at the energy lost in the system, right? We have a resistor in there, so we should have some amount of energy that's being transformed into heat. So the energy losses associated by our resistor, I want to look at it over exactly one cycle, okay? So this is going to be the integral from 0 to t of the power absorbed by my resistor as a function of time. Well, since we have a good grasp of what the current flowing through the resistor is looking like, I'm going to use the equation that P is equal to I squared times R in order to represent the power of the resistor, or the power absorbed by the resistor. So I'm going to have the integral from 0 to t of R times IL of t quantity squared. Substitute in my relationship for my inductor current, just to be really clear here. I get to use my inductor current because this is a series RLC circuit, so everything has that same current flowing through it. So that's going to be the integral from 0 to t of R times Vm over R cosine omega naught t quantity squared dt. And using relationships that we developed back in circuits 1, we know that the integral of this cosine squared term is just going to give us the magnitude divided by factor of 2, or the magnitude squared divided by a factor of 2, right? So we're going to wind up getting Vm squared times the period divided by twice R. The period of our signal is related to the angular frequency omega, right? So capital T is 2 pi over omega, again in circuits 1 relationship. And so we wind up getting here 2 pi times Vm squared divided by twice omega naught R, where this 2 pi over omega naught is just capital T. Nope. So notice here, we would have Vm squared divided by R squared multiplied by an R. We only have one R in the denominator. All right. So we now have an expression for the energy stored in our system, and we have an expression for the energy dissipated in our system per cycle, okay? So now let's define the quality factor that we talked about at the end of last class meeting, okay? Our quality factor Q is defined as 2 pi times our energy stored in our system divided by the energy lost or dissipated per cycle. And so for our system, that is literally just 2 pi times WS divided by WR, which is going to come out to be 2 pi times, let me scroll up here, Vm squared L divided by 2R squared divided by 2 pi times Vm squared divided by twice omega naught R. So this 2 pi cancels this 2 pi, this Vm squared cancels this Vm squared, this 2 cancels this 2, this R squared here gets rid of this R. And so what we're left with for our series RLC circuit is that Q is simply omega naught L divided by R. So the quality factor for our system can be expressed in terms of the inductance value and the resistance and the resonant frequency. Let's take this one step further. We know that omega naught is equal to 1 over the square root of LC, like so. So what is L divided by the square root of LC? Square root of L over square root of C, right? So this can be written as 1 over R times the square root of L over the square root of C. So now we're able to express our quality factor in terms of our component values if we don't happen to know what our resonant frequency is. And we can actually go one step further from here as well, right? So if we had omega naught R, let's see, let's put this in here. Another way to look at this expression would be to have it as L divided by R times the root of LC, right? Because 1 over LC multiplied by L over R is going to look like this. If I multiply this expression by the square root of C over the square root of C, now I have L divided by square root of L, which is just square root of L in the numerator. That's going to look like square root of L times square root of C is square root of LC divided by RC is nothing more than 1 over omega naught RC. Right? So here's one form where we need to know the inductance, the resistance, and the resonant frequency. Here's a second form where we need to know the resistance, the capacitance, and the resonant frequency. And here's a third form where we just need to know the component values and we don't need to know the resonant frequency at all. So all three of these are ways to represent our quality factor for our series RLC circuit. So any questions about any of this algebra before we move on to bigger and better things? All right. So what I want us to do now is I want us to derive the frequency response of a series RLC circuit in terms of quality factor and resonant frequency, right? So we're really starting to look at things more at a system level than we are at a circuit level here, right? Realistically, this relationship, or actually, I guess I should say it more this way. This particular relationship for Q is not particularly for circuits, it's for anything. So this is mechanical systems, all that kind of good stuff as well. So why we might have to pay attention to Q and the resonant frequency is we wouldn't want to use an electrical system at a particular frequency that would cause a linear actuator or something like that to move at its mechanical resonant frequency, or we will cause the linear actuator to tear itself apart. So anyway, so let's say that we have the following system. Here is our input signal, just a phasor voltage. Here is our inductance. Here is the impedance of our capacitance. Here is our resistance. And we're taking our output voltage for this particular system to be the voltage drop across the resistor. In a couple of minutes, we're going to look at this system again, exactly how it is, except we're going to look at the voltage drop across the capacitor to talk about a couple of things. How many of you were awake enough in circuits 2 that could tell me what this is supposed to be? Some kind of filter. Great. We'll start there. Absolutely. Any of these RLC circuits are going to be some kind of filter. This one is going to wind up being a bandpass filter. And we are going to put Q and omega naught in context and see how it relates to important filter things like bandwidth and all that kind of good stuff. So that's what we're doing here. Okay. So this is a simple voltage divider circuit. So we can see that our output voltage is just our input voltage times R divided by R plus J times omega L minus 1 over omega C. And I'm going to put this in kind of more of the standard form that we're used to. I'm going to divide by, or I guess multiply by 1 over R times 1 over R here, so that we just have a simple thing that we can figure out poles for. So this would be the same as Vn times 1 over 1 plus J times omega L over R minus 1 over omega RC. Are we okay with this level of math thus far? So what I'm going to do now is I'm going to multiply just the imaginary part of this guy by Q over Q. And so what that's going to give me is 1 over 1 plus J Q times omega L over R Q minus 1 over omega RC Q. And we're going to recall that Q can be expressed as omega naught L over R for the first term, and it can be expressed as 1 over omega naught RC for the second term. So since I'm dividing by Q here, I'm effectively multiplying this omega L over R by the reciprocal of this thing, and I'm going to find out that the L's and the R's cancel each other out, leaving me with one over 1 plus JQ times omega over omega naught. I'm going to do the same thing to the right-hand term, right? So dividing by Q is effectively just putting the reciprocal of Q here in the denominator, or excuse me, in the numerator, and the R's and C's are going to cancel each other out. And so this will look like negative omega naught over omega. From this, our transfer function, h of j omega, which is just the ratio of V out to V in, can be expressed as 1 over 1 plus JQ times omega over omega naught minus omega naught over omega. So we now have a transfer function for a circuit that is completely and utterly independent of circuit parameters. If we wanted the magnitude of our frequency response, that would be the magnitude of h of j omega, right? This is just going to be 1 over the square root of 1 plus q squared times omega over omega naught minus omega naught over omega quantity squared. And let me finish this square root. So effectively, the magnitude of the real part squared plus the magnitude of the imaginary part squared and the square root of the whole thing. That's just Pythagorean theorem, making a complex number, taking the magnitude of a complex number. Nothing particularly wild or crazy there. And the phase response as a function of omega is just going to be the inverse tangent of negative q times omega over omega naught minus omega naught over omega. Where this negative sign here, or excuse me, this negative sign right here effectively comes about because I would wind up multiplying this thing by the complex conjugate of the denominator over the complex conjugate of the denominator. I would wind up with a negative sign in the numerator, and so that's why I will get a negative sign down here in my inverse tangent function. James.
The one, like, before you have one,
No. Good question, but no. Okay, so I'm not, when I'm finding the magnitude of this thing, so let me explain it in a slightly different way, right? So if I have a complex number A that is A plus JB, the magnitude of A is the square root of A squared plus B squared. But the other way to think about it would be if I multiplied this by the complex conjugate of the denominator over the complex conjugate of the denominator, I would actually have J times negative J, which is still going to give me that plus sign. It's two ways of looking at the exact same thing. I'm just doing it what I hope to be the faster way because we've done this in 3 different classes at this point, but complex numbers are difficult. All right, so let's plot this bad boy. So on the left-hand side, let's plot my magnitude response. This is not in a logarithmic scale, just to be really clear. We can talk about what that's going to look like in just a moment. So let's say that omega naught is here in the middle. So we should have something that looks like this. Well, that'll be okay. So band pass filter like. And then over here, let's plot our phase response. So here's omega naught. This will be positive 90 degrees and negative 90 degrees like so. And we should have something going on effectively like this. So we should see that the phase angle of our response changes from positive 90 degrees at very low frequencies up to negative or down to negative 90 degrees at very high frequencies. Okay. All right. So let me specifically put this thing to be 1 right here. All right. So when we talked about filters way back in circuits 2, we defined the bandwidth to be the difference in the half power frequencies, right? Since power is related to the magnitude squared, what we're looking for effectively is when our response plot is equal to 1 over the square root of 2, right? So I'm going to draw a dashed line like so. And I can see very easily that I'm going to have 2 corner frequencies for this system. And based on what we know about the behavior of poles and all that kind of stuff from our analysis of Bode plots and all that jazz, we should also see that at these exact same frequencies is when our phase response hits exactly 45 degrees and negative 45 degrees, respectively. So now let's see if we can tie in bandwidth to quality factor and all that kind of good stuff. Okay. So I want to figure out what this frequency is and this frequency is. Let's call it omega low and omega high. Same thing here, omega low and omega high. And I know that this is going to, or these omega low and omega highs are going to happen when this guy right here is equal to 1 over the square root of 2. So that means that this denominator has to be equal to the square root of 2, or this expression q squared times omega over omega naught minus omega naught over omega must be equal to plus or minus 1, right? Because 1 plus this thing has to equal 2. So under the constraint that q times omega over omega naught minus omega naught over omega must equal to plus or minus 1, I'm going to wind up getting 4 solutions that satisfy this. Okay. I will have omega is equal to plus or minus omega naught over twice q plus or minus omega naught over 1 over 2q quantity squared plus 1. I'm going to throw away solutions that wind up giving me negative values of omega, because I can see very plainly from my graph that I expect my corner frequencies to have positive values of omega. So that seems like a reasonable way to approach this, right? So I will find then that omega low happens when I have negative omega naught over 2q plus omega naught over the square root of 1 over 2q quantity squared plus 1, or factoring out omega naught, negative 1 over 2q plus the square root of 1 over 2q squared plus 1. So this one is going to be a little lower than omega naught. And omega high is going to be positive omega naught over 2q plus omega naught times 1 over 2q quantity squared plus 1. Or omega naught times positive 1 over 2q plus the square root of 1 over 2q squared plus 1. Finally, my bandwidth is simply omega high minus omega low, which comes out to simply be omega naught over q. And this goes right back around to talking about what we had mentioned at the end of our last classroom, right? The higher the Q value we have, the more selectivity we have because our bandwidth is narrower, right? So if we want to make a filter for a system where we only want to pick up frequencies over a very, very limited range, like in our cell phones, where I don't want to be able to hear everybody else's cell phone conversations that's in the same region as my cell tower, I need a system with an extremely high Q value so that the selectivity is very, very precise, right? Same thing for our radios and our cars and all that kind of good stuff, but we get to have that bandwidth a little higher, 200 kilohertz. All right, so we have tied kind of our previous analysis for circuits, or excuse me, for filters that we did in circuits 2 back around to more universal quantities. What I want to do now is take a look at a couple of numerical examples so that we can kind of see some potential issues we might face when dealing with a resonant series RLC circuit. So, absolutely.
So are those equations for omega low and omega high going to be the same for parallel?
For omega low and omega high, I think they're going to be pretty similar. However, the definition for Q is going to be different. It's going to be the inverse of exactly what it is for, or the reciprocal of what it is for a parallel, or excuse me, a series RLC circuit. And we'll talk about that at the beginning of class on Friday. Brody. So, I believe we would wind up getting R over L for our bandwidth for a bandpass filter with just a series RLC circuit. I believe that's the results. It's either R over L or R over 2L. I don't remember off the top of my head because it's been 6 months, but yes. Things will cancel out kind of nicely and we can determine the bandwidth just in terms of our circuit parameters. Anything else before we throw some numbers? Yes, Hannah. So yes, okay. So omega naught won't be different at all, and Q won't be different at all per se. But so like if we were taking just the voltage drop across the capacitor, we would have a second order low pass filter. And so our bandwidth would define specifically to be where our circuit is above the half power frequency. We are just going to have one omega low and there will not be an omega high because we're expecting it to just roll off and stay down, right? Similarly, for a high pass filter, we actually kind of have an infinite bandwidth in as much as every frequency greater than omega high it stays above that 3 dB cutoff point. For our band stop filter, which is what we would get if we took the voltage drop across the capacitor in series with the inductor, we would have these exact same relationships, but it's actually defining the stop band, not the pass band for that particular filter. If you wanted to go back into Moodle for circuits 2, you will actually see that I explained all of that in my notes for second order filters.
Neper frequency and corner frequency are like the same. I'm sorry, this is.
No. So Neper frequency is a term that we use when we're looking at the transient analysis, and it is telling us effectively, that's our alpha, and so that's telling us how our system exponentially decays in our system. So it is analogous, but not the same thing as our time constant for first order circuits.
The only reason I asked, because you mentioned the R over L or 2L, I'm pretty sure.
R over 2L is the Neper frequency for a series RLC circuit, yes. So they come out to be a similar thing, but I don't want to say that that's a too broad. Yeah. Yeah. Where'd I put my pen thing? There we go. Any other questions before we throw some numbers at this stuff? All right. So let's look at a simple series RLC circuit. Wherein sorry, the wrong page here. We have a 10 angle 0 degrees volt source exciting this circuit at resonance. We have a 3 ohm resistor. We have a 0.1 Henry inductance. And then we have some capacitance C. And the first thing that we want to know is what value of C will place the circuit in resonance at an angular frequency of 1800 radians per second. We want to know what is the Q factor for the circuit. And then number 3 here is we want to determine the magnitude of the capacitor voltage and the magnitude of the inductor voltage at resonance. All right, so to answer part one, that's fairly straightforward, right? We know that omega naught is equal to the square root of 1 over LC. So with a little bit of algebra, we can find that C is equal to 1 over omega naught squared times L. Putting numbers into this guy, we wind up getting 3.086 microfarads. Easy peasy there. So if we were trying to design a resonant circuit, these are the kind of relationships that we would do. Our quality factor is just omega naught L over R. We know all of those things. We'll find out that this is simply 6, right? Just as a heads up, quality factor is a dimensionless quantity, so it's just the number 60. There isn't any units or anything like that that we have to concern ourselves with. The boring stuff. Now let's look at something kind of interesting. Okay. We want, yes, Brody. Because I was told that I want resonance at 1800 radians per second. So let me make this slightly more obvious and put omega naught is equal to 1800 radians per second. Yes. And so it isn't two VCs, it's VC and VL. So the voltage drop, the magnitude of the voltage drop across our capacitor and the magnitude of the voltage drop across our inductor. All right. So how are we going to find the magnitude of the voltage drop across either of these elements? Well, I would argue that we probably need to know the current flowing in the circuit. And I feel pretty strongly that that's easy to determine. Since this circuit is operating at its resonant frequency, the current I flowing around the loop is simply our source voltage divided by the resistance. So this is going to look like 10/3 angle 0 degrees. So when our circuit is operating at resonance, we don't care about the inductance nor the capacitance because we know that the resistance is the only part that's actually doing anything at that particular point in time. So the magnitude of the capacitor voltage is just going to be the magnitude of the current times the magnitude of the impedance of the capacitor. And so that's just going to look like the magnitude of I over omega naught C. I want you guys to calculate this real quick and tell me what it is. I feel like you might be incredulous, but if you calculate it, you'll agree with it. $600. So the voltage drop across the capacitor has a magnitude of 600 volts. Across our inductor, this is going to be the magnitude of I times omega naught L. Go ahead and throw that into your calculator, please. Also 600. Yep. What are the practical implications of this? we put 10 volts in. We were to take the voltage drop across our capacitor or our inductor, we get 600 volts out. What do you think the ratings for the capacitors and the inductors that you guys regularly use to make circuits are? Probably a lot less than 600 volts, right? So if you were to drive a circuit at resonance, or you were trying to design a circuit to operate at resonance because you wanted to make an amplifier or something like that, you need to be real careful about your component ratings, because at resonance, the voltage drop across your energy storage elements get really, really high. For a parallel resonant circuit, we'll see the currents get really, really high. So we could design a circuit that would operate at resonance, and then if it didn't operate the way we expect it to, it's probably because we're actively burning out the components that we're trying to do things to, right? So we really need to pay attention to whether we're operating at resonance, and whether actually, so when we're designing a system, we need to pay attention to if we're operating close to resonance, if we're not trying to operate exactly at resonance, and make sure that our components can actually handle that. Right? Yes.
So a component like wiring rated for a lot of rated 600 volts in the installation. Does it mean it's actually rated 600 volts, or is there a built-in safety factor?
I'd have to look at the NEC code, but I'd be willing to bet there's a built-in safety factor for that.
Is it the same way for like one wouldn't burn out at 23?
So for breakers and stuff like that, it's usually a safety factor of 25%. So, and I think ampacity tables effectively work that way as well. There's a 25% safety factor. Actually, no, for the ampacity tables, there's a little bit of rounding or whatever, but when you size your breakers for those cables, you add that 125% in for transients and all that kind of stuff, so that you're not constantly tripping your breakers and all that kind of stuff. But I have to look at it. The component ratings for capacitors, resistors, and inductors, typically speaking, are considering a steady state condition, but this is looking at a steady state sinusoidal circuit effectively. So this is the steady state voltage that capacitor and inductor would sustain. All right, I only have 2.5 minutes left, so we will talk about the next thing that I want to talk about. By the way, this 600 volts here for the capacitor, 600 volts for the inductor, seems really high. Not quite the actual maximum value that these guys will sustain. We'll talk about that at the beginning of class on Friday, and then get into parallel resonance.
Did you want to make?
Oh, yeah, so let me mention the MathCAD stuff really quickly. Thank you for the reminder. So I got a couple of emails about exam 2 and what is fair game and what is not fair game, and I figured this would be the easiest way to talk about stuff. I'm going to use Matthew Dickerson at, geez Louise, I get so many damn emails. So, like I said, I've gotten a couple of emails about asking what's fair game and what isn't. So what Matthew did here using MathCAD in order to get his polynomials and S and all that kind of good stuff, absolutely fair game. That is exactly what I showed you guys how to use MathCAD to do. What I don't care for is this bit right here, where he's just using MathCAD's ability to do partial fraction expansion for him to do the partial fraction expansion. So I want you guys to do that. That being said, if you took this denominator and then said solve for S to get your roots, I am absolutely okay with that, so that you don't need to do it by hand. But I don't want you to use MathCAD to do the partial fraction expansion completely for you. So you can use it to help you do the calculations to determine your expansion coefficients, but it can't just give you the expansion coefficients. And then down here, he's using the inverse Laplace transform to just do it for him as well. Also not on board with that. Okay. So use it as a tool and use it to check your answers. Don't have it just give you the answers. Are we okay with that? Well, I mean, you don't have a choice because I'm telling you that's what I want.